Hey there, it's Shannon Math Check Myers, and today we'll be checking out arc length and curvature. So this time we'll be finding arc length of a space curve, and we'll use that to describe a plane curve or space curve, and to find curvature of some curve at a point on the curve, and use a vector valued function to find frictional force. All right, so here we go. To warm it on up, we want to find the arc length of the curve, x equals arc sine of t, and y equals natural log at the square root of quantity 1 minus t squared on the interval from 0 to 1/2 inclusive. So here, why don't you see if you can kind of reach back into your brain, into Calc 2 or Calc 1, whenever you took this, and go ahead and warm it on up. All right, let's see how you did. So first off, let's rewrite just the formula for arc length. So it's a lowercase f, and that's equal to the interval from a to b of dx dt squared. And sorry, this is all under a square root plus dy dt squared with respect to t. Cool, cool? Okay, well, what is x? X is equal to arc sine at t, and so dx dt ends up being what? Beautiful. You're going to get 1 over the square root of 1 minus t squared. Now remember that, what do we want? We want that to be squared in the formula, right? So dx dt, the quantity squared, will just be 1 over 1 minus t squared, so it gets rid of that square root. Now, if you simplify, remember that y is equivalent to 1/2 natural log of quantity 1 minus t squared, using the power rule for logs. We're basically unsimplifying the log, expanding it. So we've got this, our y is 1/2 times natural log at 1 minus t squared. And so dy dt squared will be, so the 1/2 will go along for the ride, times 2t over 1 minus t squared, and that whole thing will be squared. All right, so these 2's will divide out, and so if we simplify, dy dt, the quantity squared, will be beautiful. We'll have t squared over 1 minus t squared, that quantity squared. Groovy? Okay, so now, here we go. Plugging in what we've got going on, we have what? Well, let's check it out. We have s equal to the integral from a to b. Now you've got to be careful. You've got to make sure that you only trace the curve once, because otherwise sometimes it bounces back and forth. Clear, and so you want to make sure you're in parametric mode and in radians. And now our y equal will look like this. So x at t, remember, was arc sine at t, and then y at t was equal to, I'll just write it as it originally showed up, natural log at the square root of 1 minus t squared. And I got to make sure I kept that negative in there, although the negative won't matter, right, because it'll square away, but I'll make sure I have it. Okay. I'm going to change the color of the graph so it shows up better. And let's check it out. Okay, so now what I'll do is I'm going to click on the graph. Okay, starting at 0, I'm going to go from t is 0 to 1/2 just to make sure nothing's double traced. All right, so here I'm carousing along, and notice that t isn't bouncing back and forth, and I get to t equal to 1/2 about here, right about there. And so I'm good to go. I don't need to worry about the graph doubling up on itself. Cool. So there's our picture right there if you want to check it out. But the main idea behind this one, I mean, it's good to have a picture. We're trying to find this length that goes from 0, t is 0, to t is 1/2, which is about right there. Okay, so we're looking for that arc length, and we've ascertained that it doesn't bounce back and forth on that interval. So our interval will be from 0 to 1/2, and then we will have the square root of 1 over 1 minus t squared. That was dx dt, the quantity squared. And then, by the way, remember this was a negative, this was a negative right here. And so, but when you square it, the negative goes away. So we'll have plus t squared over 1 minus t squared, the quantity squared, and that is with respect to t. Simplifying, and actually we're probably going to want to, I probably should have given you some more space. Copy this, and then C, next page. Simplifying, we will have S is equal to the integral from 0 to 1/2 of, I'm just getting a common denominator, so we need a factor of 1 minus t squared on the first term, and then we'll have plus t squared all over 1 minus t squared, the quantity squared. That's all under a square root dt. S is equal to the interval from 0 to 1/2 of 1, the square root of 1, which will just be 1, so I'll write dt in the numerator, over 1 minus t squared, because that's the square root of 1 minus t squared, the quantity squared. Now, since we did do this square root, there's a good chance that we may end up with sign change at the end. So we'll just keep that in mind. Now, how do you integrate this? This is a good review of a certain skill. Partial fraction decomposition, right? So if we do partial fraction decomposition, that'll be part of our evil plan, right? The denominator is 1 minus t squared, right? So you basically, you have this expression 1 over 1 minus t squared, but that's equivalent to 1 over 1 plus t, 1 minus t, right? So you set that equal to a, because they're linear, over 1 plus t plus b over 1 minus t. And then, getting a common denominator, you have 1 is equal to a times 1 minus t plus b times 1 plus t. Now they both have the same denominator, so you can just keep working with the numerator. So we'll get 1 is equal to a minus a times t plus b times t. Now we have 0 t's, but we have a t terms on the other side, and then we have our 1 as a constant. So here we go. So we'll have, for our t's, we have negative a plus b times t. I'm factoring the t out to the right. And then we've got plus a plus b. Cool so far? And so now we're going to be equating coefficients. So I'll equate the a plus b to that 1, and then I'll equate the negative a plus b, which is the coefficient to the t term, to 0. All right, so doing so, I'll have negative a plus b is 0. So b is equal to a. Now, from the second one, we have a plus b is 1. But I just found out that b is a, right? So a plus a is 1. 2a is 1. So a is 1/2. Cool? So here I found out that b was equal to a. So I substituted that in and solved that system of equations. So if a is 1/2, continuing, then that means b is also 1/2. Good so far? So now, coming back here, I will have s is equal to the integral from 0 to 1/2 of, so I've now found that this fraction is equal to one-half over 1 plus t, and then plus 1/2 over 1 minus t. Groovy? All right, and so now, here we go. I can factor out the 1/2, right? And I'll have 1 over 1 plus t plus 1 over 1 minus t with respect to t. So integrating, I will have 1/2 times, the first one will just be natural log absolute 1 plus t. Okay, so far? The second one I have to adjust by a negative. Okay? So I will end up with minus natural log absolute 1 minus t. And that goes from t equals 0 to t equals 1/2. So S will be equal to 1/2 times natural log absolute 1 plus 1/2 minus natural log absolute 1 plus 0 minus natural log absolute 1 minus 1/2 plus natural log absolute 1 minus 0. Cool, cool? All right, so simplifying, we'll have 1/2 times, let's see, I think we'll get natural log at 3/2 minus natural log at 1, which is 0, and then minus natural log at 1/2. This would be absolute value, right? But they're all positive. And then minus natural log absolute 1. Well, natural log 1 is 0, so we're going to end up with S is equal to 1/2 times natural log of 3/2 minus natural log of 1/2, or at 1/2. But using properties of logs, that is 1/2 times natural log at 3/2 divided by 1/2. And I dropped the absolute value because we have positive number. So, making this pretty, we will have natural log root 3 units. So that'll be in linear units. Right? Cool, cool? All right, so that is, so just a little bit over 1.7-ish is our, is the arc length of that curve. Now, of course, we are going to be extending this to space curves, right? So that one was a curve in the plane, as we saw, but we want to take a look at space curves. So the arc length of a space curve is going to be, let's see, if C is a smooth curve given by R at T is equal to X at Ti plus Y at Tj plus C at Tk on an interval from A to B inclusive, then the arc length of C, so it's going to be S is equal to the integral from A to B. And it should be real easy to remember because, again, you're going to have the derivative with respect to t of your x function, your x prime rather. So I'm going to write it as x prime at t squared, which is how we could have written dx/dt before. And then plus, good, y prime at t, the quantity squared, and then plus z prime at t, the quantity squared, and that's with respect to t. And of course, you could write this as also as the integral from a to b of the square root of the vector r prime at t with respect to t. Cool, cool? Awesome. Okay, so now let's check out an example. We want to find the arc length of the curve given by r at t is equal to 2 sine at t times I plus 5t times j plus 2 cosine t times k. And that's going from 0 to pi. And now I've got my, my tangent and my normal vectors going along as well, and my orientation. So as t increases, so you can see the dot on the edge there. And notice that it does not trace that curve more than once. Let's check it out. So here, we've got all the pieces. X at t is what? Beautiful. 2 times sine at t. And so x prime at t x prime at t, the quantity squared, will be 2 cosine at t, the quantity squared, which is 4 cosine squared at t. Groovy? All right, y at t is equal to 5t, and so y prime at t, the quantity squared, will be 5 squared, which is 25. Groovy? All right, so just so we're all good to go on these things, that was x prime at t. This here, of course, is y prime, is the 5. And then, z at t is equal to 2 times cosine at t. So z prime at t, the quantity squared, will be, awesome, negative 2 times sine at t, the quantity squared, which is positive 4 sine squared at t. And z prime at t was this. Okay, so now we know, just like the other one, we know that our s will be equal to the interval from a to b. So we found out that on the interval from 0 to pi, we don't trace more than once, right? So we're good on that. And it'll be the square root of x prime at t, the quantity squared, which was 4 cosine squared at t, and then plus 25, that was y prime at t squared, and plus 4 sine squared at t with respect to t. All right, so now s will be the interval from 0 to pi up. So I can play around with the trig identities, right? So I will get 4, if I factor out of 4 from just the cosine squared t and the sine squared t, I get cosine squared t plus sine squared t. And then I still have my plus 25 hanging around with respect to t. So we'll get s is equal to the integral from 0 to pi. Cosine squared t plus sine squared t is just 1, right? So won't I just get 4 times 1 plus 25 under that radical? You got it. So we'll have root 29, and that's with respect to t in the integrand there. So now, so easy it's hard, s will be equal to root 29 t evaluated from t equals 0 to t equals pi. So our arc length will be root 29 pi minus root 29 times 0. So s will be root 29 times pi linear units. How'd it go? Awesome! I knew you could do it. You guys are great. Okay, so arc length function. So this one was just the arc length, okay? But now you can have an actual arc length function, all right? So the arc length function, if you've got C as a smooth curve given by R at T defined on the closed interval from A to B, then the arc length of C could also be written as S in terms of T is equal to the integral from A to T of the square root of x prime at U, the quantity squared, plus y prime at U, the quantity squared, plus z prime at U, the quantity squared, with respect to U. And that, of course, is also equivalent to the integral from A to T of r prime at U squared du. Cool, cool? All right, so the arc length S is called the arc length parameter. The arc length function is non-negative as it measures the distance along C from the initial point. Using the definition of the arc length function in the second fundamental theorem of calculus, you can conclude that ds dt is equal to the magnitude of r prime at T. Note, for motion along a curve, the convenient parameter is time t. For studying geometric properties of a curve, the convenient parameter happens to be the arc length, S. Cool, cool? All right, so let's look at example 2. Find the arc length function for the line segment given by r at t equals 3 minus 3t, that quantity times I, plus 4t times j, and t rather goes between 0 and 1 inclusive. And then t is just going from 0 to 1, right? And so it looks like t equal to 0 starts here, and then I'm tracing along until t hits 1, and it looks like t equal to 1 stops right about here, right? So so again, I'm good to go. It didn't double trace our arc length. Okay. Now let's take a look. Let's use this. To find our arc length parameter, we're going to be using the ds dt equals the magnitude of r prime at t. So here, let's see what we get. So remember, r prime at t would equal to what? Beautiful. Negative 3 times I plus 4 times j. Cool so far? So now the magnitude of r prime at t would equal to the square root of each of these coefficients squared, and that is equal to 5. Now, what do we need to do? Well, we need to integrate from A to T. So 0 was my A, and we're going to go to T. And then 5 with respect to U. And that is my S at T. So that gives me that S at T equals, beautiful, 5T. Now, what you can do is this. That's written in function notation. If you write this as S is equal to 5T, and if we isolate T, we'll get S over 5. Cool so far? So, back substituting into our original R, right, we would get R at S is equal to 3 minus 3 times S over 5 times I plus 4 times S over 5 times J. So all I did was, wherever there used to be a T, I plugged in S over 5. Cool? And for T. So now, let's check it out. So, R at S will be, sorry, my 5s and my S's are very similar. So we'd have 3 minus 3 times S over 5 times I plus 4S over 5 times J. Now we need to figure out the interval, right? So remember, we had that 0 was less than or equal to T was less than or equal to 1. Well, what is T? T is S over 5 and so that means that 0 would be less than or equal to S would be less than or equal to 5. So, wrapping it all up, our function R at S is equal to 3 minus 3S over 5 times I plus 4S over 5 times J, where 0 is less than or equal to S is less than or equal to 5. And we're all done. Groovy? Now, just for fun, let's check out the magnitude of R prime at S. We found R prime at T, right? Let's find R prime at S. R prime at S is equal to, beautiful, negative 3/5 times I plus 4/5 times J. Now, if we look at the magnitude of R prime at S, that's going to be the square root of negative 3/5 squared plus 4/5 squared, which is root, let's see, 9 plus 16, do you see we'll get 25 over 25? So root 1, which is 1. So the cool thing is that's always the case. So if C is a smooth curve given by R at S equals X at S times I plus y at s times j, or in space, r at s equals x at s times I plus y at s times j plus c at s times k, where s is the arc length parameter, then it turns out that the magnitude of r prime at s is always 1, okay? Moreover, if t is any parameter for the vector valued function r such that r prime at s is the magnitude of r prime at s is 1, then that implies that t must be the arc length parameter. So basically, in logic, right, if you've got a parameter t for a vector valued function r, and it's given that r prime at s is 1, the magnitude of that is 1, then that implies t must be the arc length parameter. Cool, cool? All right, so definition of curvature. Let C be a smooth curve in the plane or in space given by r at s, where s is the arc length parameter. So we know magnitude of r prime at s is, awesome, 1. The curvature K at s is given by K is equal to the magnitude of d ds of the tangent vector, which is equivalent to the magnitude of the tangent vector prime at s. Cool, cool? Okay, so now we're putting together more stuff. If you recall, so our evil plan, remember, is that t, the t vector in terms of s would be, beautiful, r prime at s divided by the magnitude of r prime at s. We've got our unit tangent vector. Good so far? All right, so let's check it out. R prime at s is going to be I. 1i plus 0j, right? And so what will happen? We get the vector 1, 0, right? So we get t is equal to 1, 0, which is our r prime at s, divided by the magnitude of 1, 0, which of course is just going to be I, 1, 0, or I. Okay, well, differentiating this, what do we have? K is equal to the magnitude of t prime at s, right? Well, t prime is going to be what? Beautiful. 0, right? So we'd have the magnitude of 0, actually the 0 vector, which is always 0. Cool, cool? So there's no curvature. All right, awesome. So if t is 3 plus s, I mean, in reality, I'm trying to figure out the domain, you know, in range for s. Then basically s would start at -3, right? So if we start our t min at -3, then what's going to, and our range, our output of this is always going to be 1. right? Because one is the coefficient of our j term. So we will have a situation where we have just a parallel line, right? Starting at 0, 1. Cool? So that's what that one looks like. And then now, if we trace, do you see that it just keeps going on? It's never going to bounce back on itself. Okay? So as you can see, there is no curvature. And so that 0 curvature makes sense. Cool? All right, so now moving right along, formulas for curvature. If C is a smooth curve given by R at T, then the curvature K of C at T is given by. You can either do there's a couple you can do, and it just depends on what information you have. So K is equal to the magnitude of T prime at T divided by the magnitude of R prime at T. But that in turn is also equal to the magnitude of R prime at T cross R double prime at T over the magnitude of R prime at T, the quantity cubed. So basically, this first formula is the ratio of the rate of change of the unit tangent vector, right, compared to the rate of change of the arc length. So basically, the greater the length of the change in the unit tangent vector, the more the curve bends at T. All right, so let's take a look. Finding the curvature K of the curve R at T equals 2t squared I plus tj plus 1/2 t squared k. So if we animate our T, it goes along the curve like this, right? And so checking out our curvature, it just depends on which route you want to go. Let's go ahead and practice cross product. And we just need our R prime and R double prime at T. This example, it's going to make it fairly easy, right? Because we've got small positive integers as powers. So R prime at T is equal to 4t I plus 1 times j plus t times k. And then R double prime at T will be 4i plus k. Cool? All right, so that formula that we're using is that K equals the magnitude of R prime at T cross R double prime at T, that the magnitude of all that, all over the magnitude of R prime at T cubed, that quantity cubed. So let's find everything out. This one here, the magnitude of R prime at T is just going to be equal to, let's see, so this is going to be the square root of, 4t quantity squared is 16t squared, and then plus 1 plus t squared. So we can rewrite that as 16t squared plus t squared plus 1 raised to the 1/2. Cool so far? Awesome. Now, r prime, this cross product, right? So r prime at t cross r double prime at t is going to equal to I, j, k. And then let's see, our prime vector is what? We'll have 4t, 1, and t. And then we'll have for our double prime 4, 0, 1. So I'm going to go and expand about the one that has the 0. So this would be plus, minus, plus, minus, plus. So we're going to expand about this row. So we will get 4 times the determinant of j, k, 1, and t. And then the second one zeroes out, and then we'll have plus 1 times the determinant of ij, and then 4t and 1. So that's going to end up being 4 times t times j minus k, and then plus I minus 4j. And so that's going to give us, let's see, it looks like our j's are going to zero out, and so we'll end up with 1i minus 4k. So now if we do the magnitude of I minus 4k, that's equal to the magnitude of 1, 0, 4, which will be the square root of 1 plus 16, which is root 17. Cool so far? Now, oh look, I forgot to simplify this one here, up here. We've got like terms of the t squared. 17t squared plus 1 raised to the 1/2. All right, so now here we go. K will be equal to, so the numerator is going to be the square root of 17, the magnitude of r prime at t cross r double prime at t, over the magnitude of r prime at t raised to the 3rd power. So we would have 17t squared plus 1 to the 1/2, all of that cubed. So k will be root 17 over 17 t squared plus 1 raised to the 3/2. And we're done. So at any given time of t, you can find out what your curvature is. Okay. So when t is 0, our curvature would be root 17, I believe, right? And so you basically end up with this nice function of t. Groovy? All right, so next up we have, if c is the graph of a twice differentiable function given by y equals f of x, then the curvature k at the point xy is given by k equals the absolute value of y double prime divided by 1 plus y prime squared, that quantity raised to the 3/2. Here's some related stuff. Let C be a curve with curvature k at point P. So it turns out the circle passing through the point P with radius r equals 1 over k is called the circle of curvature if the circle lies on the concave side of the curve and shares a common tangent line with the curve at point P. The radius is called the radius of curvature at P, and the center of the circle is called the center of curvature. All right? So, let's check this out. So in general, right, what you have is something like this. Oops. Okay, so let's say this is x and this is y. And let's say you have some plane curve. And, you know, let's say it looks like something like this, right? So now, if you take a look at, you know, this circle, so we'll draw a circle here. Love how that works, right? So you've got, you know, this circle of curvature. And actually, let's do this. Let's move it over here so you can really get a feel for it. Okay. So you've got this circle of curvature, right? And let's suppose that this here is our point P, and we've got our center of our circle is about here. And so this right here would be the radius of curvature. And then over here, that's our center of curvature. Thank you, Einstein. And our curvature, so this right here would be r equal to 1 over k, which is our radius of curvature. Cool, cool? Okay, so now let's look at this problem here. All right, so find the curvature and radius of curvature of the plane curve y equals 2x plus 4 over x at x equal to 1. So remember, we're going to need to find this stuff. So k is the absolute value of y double prime divided by one plus y prime is squared, raised to the 3/2. Y prime at x, we've got it in terms of x, is equal to what? Beautiful. 2 minus 4 over x squared. Y double prime at x will just be positive 8 over x cubed. Cool so far? Okay. So, what do we need to find? We need to find y prime at 1, because x is 1. And so that's just going to be 2 minus 4 over 1 squared, which will be -2. And then y double prime at 1 will be 8 over 1 cubed, which is 8. So for x equal to 1, our k will be the absolute value of 8 divided by (1) plus -2 squared raised to the 3/2. So k will be, absolute value of 8 is 8, and then we'll get over 5 to the 3/2. And that's our curvature when x is 1. Cool, cool? All right. So now, acceleration, speed, and curvature. If r at t is the position vector for a smooth curve C, then the acceleration vector is given by a at t is equal to d squared s over ds squared of our unit tangent vector plus k times ds dt, the quantity squared, times our principal unit normal vector, where k is the curvature of C and ds dt is the speed. So now, frictional force. A moving object with mass m is in contact with a stationary object. The total force required to produce an acceleration a along a given path is, the force vector is equal to the mass times the acceleration vector. So that in turn will be equal to m, and then I'm just going to plug in our acceleration vector, d squared s over dt squared of the unit tangent vector t plus our curvature k times ds dt, our speed, right, squared times normal vector n. Good so far? But what is all that stuff? Well, the force would end up being equal to, but this in turn will be the mass times our tangential component of acceleration times the unit tangent vector plus m times the normal component of acceleration times our principal unit normal vector. Cool, cool? All right, so let's look at an example of this. This is very relevant. So a 6,400-pound vehicle is driven at a speed of 35 miles per hour on a circular interchange of radius 250 feet. To keep the vehicle from skidding off course, what frictional force must the road surface exert on the tires? All right? So, well, the mass is 6,400 pounds, right? Its speed, ds dt, is equal to 35 miles per hour. And then we don't know what k is, right? So we'll just say that k is 1 over r. But we've got this circular interchange of radius 250 feet, right? So if you think about it, you've got something like this going on. You've got a circle, right? And this radius is 250 feet. And then you've got, your truck is right here carousing along. And you want it to stay on this road. Okay, so here's your truck. I'm not an artist. All right, so okay, so we've got a situation like that. So we do know, therefore, that k would be 1 over 250. Good so far? And that's 1 over 250 feet. Now the frictional force is going to have to be which part of the force. I mean, we're not worried about the tangential, right? We're worried about the force needed for this truck to stay on the road, right? And so what we need for this particular problem is going to be the second part, right? So we're going to need m times k times ds dt, the quantity squared. So basically it just simplifies to our mass times our curvature times the speed squared, right? So this will end up being, our mass was 6,400 pounds times k, which was 1 over 250 feet, and then times our speed squared, so that would be 35 miles per hour squared. Good so far? So let's go ahead and get this in the same units. We'll end up with foot-pounds per second squared. So here, reducing a little, I think we would end up with 128 fifths, and then we have our pounds and feet, all right, times 35 miles per 1 hour, and then we'd have times, let's see, there are 5,280 feet per 1 mile. And then there are, let's see, per every 1 hour, there are 3,600 seconds. And that part's all squared. So we will end up getting 128 over 5. And again, that is pounds in the numerator, feet in the denominator, times, inside here, this reduced to 154 thirds. And then that, of course, was in feet per second. And that's squared. 67,458.8. And we end up with the pounds stay. The foot in the denominator divides out. So you end up with linear foot, well, not really linear, but it's foot pounds per second squared. And so that's how much force needs to be applied to keep this truck on the road. That's how much frictional force. Cool, cool? All right, well, that's it for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe. Bye.